Hello everyone. In today's class, we are going to see the main concept of fluid mechanics. So the flow kinematics we are going to see today in the aerodynamics class. Okay. So let's first try to understand that what is flow kinematics. Okay. And why do we need to study that? So why flow kinematics is very important? What is the unique capability that fluid is having? Hence we need to deep dive into the flow kinematics part. And what are the different ways flow kinematics can be evaluated? There are basically two different approaches for fluids to be evaluated. And what is the most common approach that we use today, right? So we are right now we are using the control volume approach, right? And any analysis in fluid mechanics is generally done most commonly used by the control volume method approach, right? So we'll see what is control volume approach and what is the alternative for that, why that alternative is not being used most popularly. So all those reasons, and how come both will be the same, whether both will give the same result or not if you do a control volume approach or a control mass approach, whether both will give the same approach or not, result or not. So all these things we will study today. Okay. Okay. With no further delay, we can get into today's topic. So what is flow kinematics? So flow kinematics is nothing but anything that changes during the flow, right? For example, when a fluid particle is in motion, right? What are the change that it experiences is called flow kinematics. What do I mean by that? Say for example, let's draw a aerofoil figure here. Okay, let's draw an aerofoil figure here. And let's say the flow is flowing like this. Okay, let's assume that the flow is flowing like this. So suddenly if you see the fluid particle, right, when it goes here, right, it will get accelerated during this part of the aerofoil. Okay, it will get accelerated during this part of the aerofoil, and then suddenly after some time it will get decelerated. And if the aerofoil is too much cusped aerofoil, what will happen, or too much curvature is given, unsymmetrical aerofoil, then there might be a chance for the flow to get separated like this. Or if there is nominally or optimally cusped and curved aerofoil, it will not get separated, but definitely the flow will get decelerated and it will slowly come down out like this. So these are the things which are available. Okay, so these changes needs to be captured in the studies. What do I mean by that is how every fluid particle, when it passes over an object, it could be an object or it could be a normal flow, whatever it is, not necessarily it has to be an aerofoil, even it could be a circular cylinder like this also, it's okay. How does the fluid particle is going to get changed? What is the experience the fluid particle is having in terms of velocity, in terms of the pressure, in terms of the temperature? It could be any property, any flow property. Okay, so what is the change in the flow property because of the different experience the fluid particle has at different location? The major difference between the fluid mechanics and solid mechanics, let's assume that if you are traveling from one place to another place, let's assume that you are traveling from Bangalore to Goa, and if a car is started, a car is a solid object, right? So and if car gets started at point B, which is Bangalore, and if it is moving to points G, which is Goa, if you want to calculate what is the um, acceleration or what is the velocity of the car, right, what will you do? You will say that, okay, you will note the time at which it started, maybe time is equal to 0, and you will note the time at which it reached Goa, maybe time is equal to maybe 10 hours, so the delta is 10 hours. And then what will happen, and you know the distance between the Bangalore to and Goa, which might be some x kilometers. Then how do you get the velocity? Velocity is equal to distance by time, x by t. This will give you the velocity. And if you wanted to know the acceleration of the car, what will you do? It's again very simple. Acceleration is nothing but velocity divided by distance. Any rate of change of velocity is acceleration. So if you want to know the acceleration of the car, you will get a acceleration is equal to, you already know the velocity, so velocity is x by t, and again divided by t, which is nothing but acceleration is equal to v by t, right? It is as simple as that, right? Because the car will, the only independent variable here is time. Time is the only independent variable, and you are going to see how much time it has taken to cover a specified distance x. Through that you can calculate the velocity of the car throughout, maybe an average velocity or whatever it is. But the same principle will not work in fluid mechanics. I will tell you why. If you understand this, then the flow kinematics, you will know why flow kinematics is very important. Let's assume that this is point B, which is Bangalore. Let's assume that this is point G, which is Goa. Okay. I'm just putting some hypothetical cases here. Okay. Or you can just assume point B and C. When a fluid particle is trying to travel from this point to this point, probably if you know the distance between this point, right, B and G. So let's assume that the distance is x. And if you noted down, when a fluid particle started here, time is equal to 0. And when a fluid particle reached here, what is the time? So x by t, if you put what is the time, you might think you have got the velocity, but this might be an average velocity, but the fluid particle has its ability to convect over the solid surface, which means what? Depends on the shape of the object it is flowing through. If it's a circle, it's different. If it's an aerofoil, it is different. Whereas if it's a bluff body like a square and all, it will be different. The fluid particle will get accelerated at every point, and after some time it will get decelerated at every point. That effect will not be taken, which means what? The velocity is not just the function of time alone for a fluid particle, whereas it is also the function of space. Okay, whereas it's also the function of space, which means what? If an aerofoil is like this, if this is x1 comma y1, and if this is x2 comma y2, the velocity at x1 comma y1, the same fluid particle, when it comes here, right, the velocity will be different because of the convecting nature of the fluid. It will convect through this solid object. Because of this shape of the object, it will get accelerated or decelerated, depends on the shape. Okay, that, which means what? The fluid properties are getting changed at different locations, whereas when you travel from Bangalore to Goa, the car property is not going to change from different location. As soon as you press your accelerator, you have all the control to maintain the speed of the car. Whereas in a fluid particle, you don't have all the control to maintain the fluid particle. The fluid particle speeds depends on every location, spatial location. What do I mean by spatial location? At every different location, here, when the fluid particle passes through the object at different location, it will either be subjected to acceleration or deceleration. That's what I wanted to make here. Because of this, the derivative with respect to time to the fluid particle is not that straightforward as we have seen in the car case here. Okay, it is, we also need to consider any change in flow, not only with respect to time, also with respect to the space. Because of the reason, the fluid particle will get convected as it moves through the solid object. Either it will get accelerated or it will get decelerated. So now you understand the major difference between the solid world and the fluid world, right? When the fluid particle goes, it will get convected, and you have to calculate, or you have to take care of the spatial changes as well. Not only time derivative, there is a spatial derivative as well. So how are we going to convert this into a mathematical form? How are we going to approach this so that you know whenever a fluid particle flows through an object, you know that okay, at this location this is the velocity, at this location this is the, you need to get an expression. You need to convert this physics into a mathematical model so that we can design our products. So let's start with that. Okay, so basically, to know the basic property of the fluid particle is velocity, okay, and pressure. So basically, if you know the velocity change, then obviously the pressure can be calculated using Bernoulli's equations and so on, right? So how does the velocity is getting varied at every location? But don't restrict yourself only with velocity. It could be anything. It could be momentum, it could be velocity, it could be acceleration, it could be anything, temperature, like that, right? But generally, it will be a great achievement if you know that okay, what is the change in velocity at every point of a fluid particle when it passes through this object. Okay, so I hope now you understand what is flow kinematics, why we are so much interested. and how it is different from solid mechanics to fluid mechanics world. Now, to understand this, right, how does the change in velocity in every fluid particle or change in flow property for every fluid particle at different location, how do we calculate this? So basically there are two approaches, right? So if you remember that basically two approaches, one is the Lagrangian approach and the other one is the Eulerian approach. Eulerian approach. If you ask me which is the right approach, both of them are right. It's not that one approach is wrong and one approach is right. No, both of them are correct. But we majorly use what? We majorly use Eulerian approach, which is called control volume approach. Okay. This Lagrangian approach is called control mass approach. Eulerian approach is called control volume approach, and Lagrangian approach is called control mass approach. Okay. So first let's try to understand, before we get into the mathematical modeling or derivation of this, first let's try to understand what is Lagrangian approach means. How Lagrangian has tried to capture this change in fluid property or parameter over every different locations. That is the first aspect. And what are the things that he has taken into account? Then similarly, we'll try to understand how Eulerian has approached, because both of them wanted to know what is the change in velocity or what is the change in any parameter for that matter for a fluid particle when it flows from one place to other place, right? But both of them has taken different approach. Let's understand first what is Lagrangian approach, then what is Eulerian approach. From there we can move further to evaluate it mathematically. Okay, Lagrangian approach is very simple and straightforward. Okay, the description is very simple. Instead of, if there is a aerofoil like this, right? Instead of fixing the position of the aerofoil, what Lagrangian has said is, let's fix a particular particle, because for example there will be n number of at a given time, right? There will be n number of fluid particles that will flow like this, right? For example, every cross mark here is the different fluid particle. There will be n number of fluid particles which will be flowing like this, right? Correct. Instead of the, out of this n number of fluid particle, what Lagrangian said is, let's only choose one particular, let's only choose one particular fluid particle. Let's fix one fluid particles and we'll try to follow that fluid particle. Instead of fixing the space, let me fix the mass, one particular fluid particle, and I will try to follow this, track this fluid particle. Then I know, okay, what is the velocity at this point, what is the velocity at this point, what is the velocity at this point. As the fluid particle travels, right, I know what is the velocity of the fluid particle at every location over a period of time if I track one fluid particle. That's the approach of Lagrangian. Here the only dependent variable is time, because here, for example, the property of the fluid particle, say, let's right now we can put this, okay, say F is the property of the fluid. It could be anything, momentum, acceleration, whatever it is. Okay, if the property of the fluid particle is F, how does it will get varied? F will be only the function of x of t, comma y of t, comma z of t, comma t. I will explain what is this. X of t is, as I told you earlier, at every location the property will get changed. How do you capture that every location? Here that every location is captured in terms of time, because if you select one particle and if you follow one particle, right, when time is equal to 0, the particle might be here. At that time the location may be x1, y1, z1. When time is equal to 5, the same particle would have come here. Here time is equal to 5, location may be x2, y2, z2. So what essentially Lagrangian is saying is, the space, the change in space is also the function of time. So x will also change. Initially x was x1 when time is equal to 0. And then when time is equal to 5, x is equal to x2, y2 is at 2. So where x, y, z is also the function of time. And also there is one more extra time. You all know what is this function. So this is called, apart from the change in space, change in location of the particle over the time, if any other external forces adds acceleration or deceleration to this flow path or to this particular particle, that change is captured through this time. Okay, so the spatial part is also captured through the time, and any external, that's the unsteadiness of the flow. If somebody is blowing some extra force into the flow for every 10 seconds, once in every 10 seconds or once in every 20 seconds, so depends on time, the flow acceleration or deceleration will get happen, right? Because somebody is coming and blowing for every 10 seconds, for example, I'm telling. So that kind of external unsteadiness will be taken care of this time part. The change, because the fluid is flowing, it will change its spatial locations over a period of time. That change in space is also a function of time. So that's what Lagrangian approach. So ultimately what will happen? F will be only a function of time. And this F could be anything. It could be velocity, whatever it is. Okay, it could be velocity or so. Ultimately, according to Lagrangian, let's consider F to be only a function of time, and the only independent variable is time. Even the space is also going to get changed over a period of time. That is true only, right? If you consider only one particle, and if you don't fix your location, but if you fix your particle and if you travel behind your particle, over a period of time, the particle at time is equal to 0, it will be in one location. After some time, it will be in a different location, right? So that's what he's saying. And if you get this function, right? If you get velocity as a function of time, and if you just differentiate this, right? dv by dt, and if you get this v of t as a function of time, then you will get what is your acceleration. The change in velocity is acceleration, right? But the problem in Lagrangian approach, or the challenge in Lagrangian approach, getting this function is not that easy. Tracking a particular fluid particle and understanding what is the velocity of that particular fluid particle at every different n number of location over a period of time is very difficult. And you need to know at which location it started. You need to know what is the initial location at which it started, and what is the final location that you are chasing, and what is the change in distance that covered, and what is the change in velocity at every location. Tracking one particular fluid particle over a period of time and noting down its velocity throughout is not that easy. Okay, but if you get that function, then it is easy. It's as good as a car, right? Because your change in space is also baked inside this, right? The change in, see, x of t, y of t, z of t is also finally baked in the form of time. So you can get your velocity or acceleration, whatever it is. That is one part. So Lagrangian has proposed this. The second one is Eulerian approach. What did Eulerian say? In that might be a little difficult. What Eulerian said is, let's do one more thing. Let's fix this space like this. Okay, and let's call this as a control limb. Instead of fixing the fluid particle, instead of fixing one particular mass and tracking behind that, let's fix this space. What is the space? This is the control volume, and let all the fluid particles flow here. So I am only interested with what is happening at every location in this control volume, in the space. I'm fixing my space. Instead of tracking an individual fluid particle or an element, we focus on a specific location. That specific location is control volume here. See, the specific location is nothing but from here to here. This is the specific location. Okay, and then here the property of the fluid, which is F, let's call it F or V or whatever it is. It will be a function of X, Y, Z and time t. And this time is nothing but the external force that I told you, right? This will be common in both the Eulerian approach and Lagrangian approach. This will only tell you whether the flow is steady or unsteady. If somebody is externally coming and blowing the flow or stopping the flow at a regular interval or whatever it is, and if you know the function of that, at what interval they are doing it, then this is called unsteady flow, and that needs to be added here. Apart from that, here what is the story that we are making here is, instead of doing this, what we are trying to do here is the flow parameter here, right? The flow parameter is not going to get changed with respect to time here. It's going to get changed only with respect to space, because the difference between the Lagrangian approach and Euler approach is, instead of following a particular fluid particle, now you fix the volume, and at a given time t is equal to 0, whatever it is, let's see what is the velocity of this particular particle here. What is the velocity here? Here means x1, y1. At some other location is x2, y2. Some other location is x3, y3, like that. So let's get the expression for what is the velocity at a given time, when the time is fixed. Whereas in the previous case, time is not fixed, right? You have to travel along with the located fluid particle, along with the specific fluid particle, and understand where the time will move from 1, 2, 3, like that. Here, that's not the case. Let's fix the time and let's see at the given time what is the velocity of different fluid particle at different space. So basically, if I know what is the velocity of the fluid particle at a given time at different location, that will also going to give me the same thing, right? Because if I follow this fluid particle, and if this fluid particle is going to follow this track, when the fluid particle comes and reach here, it will also have the same velocity here, right? What do I mean by that is, let's take a aerofoil here. Let's put particle 1 and particle 2. So particle 1 is coming like this, particle 2 is coming. So particle 2 only first go faster, right? So when particle 2 passes this point, what is the velocity that particle 2 experienced when it passing through this particular point? Let's put this point as x1, y1. When particle 1 also is coming to pass this point, right? Both the particle 1 and 2 will have the same velocity when they pass through the same point x1 and y2. Then, because of the different shape of the aerofoil, when the particle passes through a different point, let's say x2 and y2, 2 will have a different velocity. 2 was having some velocity here at x1 and y2. The same 2 will have a different velocity now at a different location x2 and y2. But now 1 will also have the same velocity here. What is the velocity that particle 2 has experienced at the location x2, y2? 1 will also have the same velocity when it passes through this fixed location. So basically the idea here is, any particle that is passing through a fixed location will have a same velocity. So the velocity is a function of space here. So the change in velocity or any fluid parameter, not necessarily velocity. You don't need to restrict yourself only with the velocity. It could be anything, momentum, anything. So that's the basically two different approaches from Lagrangian and Eulerian to understand the flow kinematics. What is the change, or what is the experience in fluid particle when it passes through the object, because of the nature of the fluid that will convict around the solid object. Because of the shape of the solid object, it might get accelerated or decelerated. How to capture that? So both has proposed this idea. Control volume approach is relatively much easier than the control mass approach, which is the Lagrangian approach. The reason is, control mass, you have to track a fluid particle and get the velocity of the fluid particle at every time period. Okay, and the space is also going to be a function of time period. Is really difficult. Instead of that, you fix a location, you focus your camera on that location, understand at a given time what is the velocity at every different location. Even though it is different particle, that's okay, because any particle which is going to pass through the same location is going to have the same velocity. So control volume approach seems to be much easier to crack any analysis than the control mass approach. That's why most commonly we use control volume approach. Now let's understand this in a very detailed way with this diagram that I have put here along with the derivations. It's very easy, don't worry about it. So the first one is the Eulerian approach. Okay, the first one is the Eulerian approach, and the second one is the Lagrangian approach. I will explain this in a minute. Okay, so what is happening here is, let's take here the time period is fixed now. Time is equal to 0 now, and a snapshot is taken. You know, S vector is nothing but the position vector. So you can call your S vector to be x comma y comma z. Okay, x vector is the position of the fluid particle. This cube is the fluid particle. Okay, when time is equal to 0, so let's assume this particle is P1, this particle is P2, this particle is P3. So what I'm trying to say is all of them are different particle. Time is fixed now, time is 0, a snapshot has been taken. What happened? This at location S0, the fluid particle P1 is having a velocity vector like this, you see. So which means that it is going to move like this. So this is the velocity at the space S0. X0 is nothing but x0, y0, z0. S1 is nothing but x1, y1, z1. So it's the location. At the same time, at a different location S1, there is a different particle which is P2, which is having a velocity vector v1. Because of the change in this location, right? See here the time is same. In the first A case, the time is same, right? Time is equal to 0. I have fixed the time. The only difference here is what? The space. S0 is different location, S1 is a different location. So the particle which is at S0 is having a velocity v0, whereas particle at S1 is having a velocity v1. And you see the velocity vector, here the velocity vector is going like this, here the velocity vector is going like this. Here after some time, sorry, at a different location S2, here the velocity is going like this. This is what Eulerian is telling. So let's understand what is the velocity at this location. So what will happen next time when now time is equal to 0, when time is equal to t is equal to 1, what will happen? P1 will come here, right? P1 will come here and P2 will go here and P3 will go further, and some other particle P0 might come here. Any particle which is going to pass through now S1 will have the same velocity V1. Any particle which is going to pass through the space S2 is going to have the same velocity V2. Any particle which is going to pass through the location S0 is going to have the same velocity V0. So that's the whole idea. You don't need to track the particle. You just fix the location, focus your camera that, understand that. Okay. So here, the only change is very simple here. Okay. The change is only the space, not the time. Whereas the same case, now if you wanted to track the same trajectory by Lagrangian approach, the second case, right, this B1, you see what is happening now? Here time is not fixed. So your particle is fixed. So this is your particle P1, and this is the same particle P1, and this is also same particle P1. Whereas here time is equal to 0, here time is equal to 1, maybe time is equal to 2 here. What is happening? At location S0, the particle is getting started and it is moving like this. It is going to move like this. At time is equal to 0, the particle is here. Okay, at time is equal to 0, the particle is here and it is going to move like this. When time become 1, it moved like this and the particle reached here, but the same particle P1. The particle was previously here. So this is S1 now and this is S0. Okay. When time is equal to 1, the particle is now here and it is going to move like this. You see, it moved like this, then it is going to move like this, then it is going to go like this. So from time is equal to 1, the same particle is here and it is going to move like this. So what is happening now? Now the particle reached here. So this is nothing but your S2. Your S2. See? This location of the particle is now S2. But now the particle is same. P1 is, but time is different. So you are tracking the same part. So now if you want to draw a trajectory, how do you draw? When time is equal to 0, the particle is here. When time is equal to 1 the particle is here, time is equal to 2 the particle is here. So both of them will give you the same trajectory. Here you calculate that using the space, even though it is different particle. Here you calculate that using a particle, tracking a particle by moving along with the particle. Okay, by moving along with the particle. That way it is, both of them will give you the right answer, but the second approach is very difficult, because tracking a particle is not that easy and measuring its velocity at every different location is not that easy. Whereas fixing the space and fixing the locations, and any particle which passes through that point, you get the velocity, so that you know, okay, any particle which is going to pass through a different location is going to have different velocity, and I know that profile. That's it. Okay, so here in the Lagrangian approach, if you want to calculate the change in velocity or whatever it is, right, dv by dt is nothing but dv vector by dt, whereas here v is a function of x of t comma y of t comma z of t comma t. This will give you the change in velocity. Or if you're not interested in velocity, you can put any property of here. Whereas in Eulerian approach, that's not the case. So your dv by dt or change in velocity. Well, let's start with change in velocity. dv is equal to a function of, since v is a function of x comma y comma z comma t. How will you write this? Dou v by dou x into dx plus dou v by dou y into dy plus dou v by dou z into dz plus dou v by dou t. So this t is the unsteady term, I told you, right? If this is not with respect to location, this is with respect to if somebody is externally accelerating or decelerating on a timely basis, that part is being taken care. Now if you divide this entire equation by time dt, right, here and here, what will happen? You'll get dt here, you'll get dt here, get dt here, yes, into dt by dt. So what will happen? Dx by dt will become u vector, u, velocity along x direction. Dy by dt will become v, velocity along y direction. dz by dt will become w, velocity along z direction. Hence your dv vector by dt, which is nothing but your total derivative, dv vector by dt is equal to, so let me write in this new page, dv vector by dt is equal to dou v vector by dou t plus u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z. So Eulerian approach gave us that two kinds of change. The first, this change is called local derivative, local derivative, and this is considered as the unsteady term. If your flow is steady, then the local derivative will be 0. If the flow is unsteady, then the local derivative will come into picture. Whereas this part is called convective derivative. I told you, right, fluid has the property to convect along with the solid object, right? So this is called convective derivative, which is nothing but the derivation that is, or the change that is happening because of the spatial difference. If you see in this figure, right, everything is fixed here. Only the velocities get, see here the velocity vector is like this, here the velocity vector is like this, here the only difference here is the space. At S0 velocity vector is like this, at S1 the velocity vector is like this, at S2 the velocity vector is like that, but time is same here. So that spatial part change is covered using the derivative u into dou v by dou x plus v into dou v by dou y plus w into dou v by dou z. This part is called convective derivative, and I told you, right, how it has come. Dx by dt will become t. So what does this mean? If you want to write this in the vector form, dou v by dou t, your total derivative is equal to local derivative plus convective derivative. Local derivative is very straightforward. Dou v by dou t plus u v vector, actually v vector dot del vector into v vector. If you expand this, you will get this form. Okay, because you will get three equations. If you expand this, you will get, because you see this is also vector, this is also vector, and this is also vector. Okay, if you want the velocity, but you can put anything here. This is actually f, any fluid property. In this case, the case now we have considered as vector. So then you will get three different equations. If you expand this, you know, right, what is del operator? It's a mathematical operator. So del is nothing, del vector is nothing but dou by dou x I vector plus dou by dou y j vector plus dou by dou z k vector. So similar like this one. Okay, so I have simplified that and written in the form of vector, and this UVW is coming from here, and what is the change that you are looking for? That is here. So this, don't get, I hope you all know that this UVW is the component of vector, right? So because the capital velocity vector v vector I mentioned is ui vector plus vj vector plus w k vector. So that is this one, that is this one. Okay, the v vector that I mentioned here is, it's a vector, it's not just one velocity component. It will have x component u, y component v, and z component w. Okay, so like that it will go. So now I hope you understand what is Eulerian approach, what is Lagrangian approach, and how we have got the Lagrangian derivative here, right? So now let's, if you expand this, right, if you expand in vector form, right, because this will have a 3 vector and this will have vector, this will also have vector, you will get, what is dv by dt? Is nothing but acceleration, right? The rate of change of velocity is nothing but acceleration. If you wanted to know the acceleration of the fluid particle, then that you will get a three direction acceleration. Along x direction, what is the acceleration? Along y direction, that is what is the acceleration? Along z direction, what is the acceleration? That is given here. So the v vector is I u vector plus j v vector plus kw vector, and if you substitute this v vector into this equation, which is dou v vector by dou t is equal to dou vt by dou t, and if you substitute this, you will get ay because you will get three equations, right? Because this is a vector equation. So your acceleration vector, which is nothing but dv vector by dt is equal to ax I vector plus ay j vector plus az k vector. Okay, so like that it will go. If the flow is one dimensional, which means that in your velocity vector you will have only u component, there is no v component or no w component, then the only acceleration component is this one. Okay, generally the flows will be, we'll treat the flow to be unidirectional. Okay, especially when they ask problems in gate and all, they will generally consider the flow to be unidirectional and they will go like that. Okay, but If you substitute all the vector forms in this equation, right, you'll finally get this. I'll write this final derivative equation. The total derivative is equal to, it could be, see, this cannot be not necessarily v, it could be anything. Okay, just in to understand it, I have put v, which is dou v vector by dou t plus v vector dot del vector into v vector. So just that I have converted this form into the vector form because we have three vectors. And if you substitute the v vector to be ui vector plus vj vector plus wk vector, you will get this three different equation: acceleration in x direction, acceleration in y direction, acceleration in z direction. Okay. With this understanding, now let's get into the problem. Some previous year gate questions problem so that you know. A fluid with volumetric flow rate of 5 meter cube per second enters the nozzle through whose cross-sectional area varies from x as a of x equal to 1 by 1 plus x square, assuming that the flow is parallel and it uniform across each section. The acceleration at any point in the nozzle is given by. So what they have given the volumetric flow rate and they have given the area. Okay, you all know volumetric flow rate is denoted by Q. So Q they have given. Volumetric flow rate is 5 meter cube per second. That's what is given here. And they also told area is not constant, area is varying, which means what? It's a nozzle, so area might vary like this. Okay, the flow might be glowing like this, but you know, area here, the area might be more. As it goes towards, the area is going to be less. So this might be the x direction, so it's a nozzle. So that's why the cross section is also varying along with the x. Now they are asking what is the acceleration at any point in the fluid. We just studied how to calculate the acceleration, right? Using the Eulerian approach, we know that we have to calculate acceleration through this, right? So what is now acceleration? To calculate acceleration, what do you need? A, and it is a unidirectional flow because they have clearly told that area is only a function of x. And if you calculate what is q, q is equal to area into velocity. Now if you calculate velocity, how will you get it? Because to calculate acceleration you need velocity. So velocity, which implies velocity is equal to q by a. Q is already given, which is 5. A is nothing but 1 divided by 1 plus x square. So ultimately you will get your v to be 5 into 1 plus x square. That's your v, right? Is meter per second. Now to get the acceleration, what are the three different acceleration here? Ax, Ay, Az, but it is an unidirectional flow because only x is involved, no y or no z is involved. So it's only x is involved. So this is no more a vector, it's become a scalar. So it's only u component is available here. This v vector is nothing but the u component here. So to find out what is the acceleration along the x direction, so we know the formula, right? Dou v by dou t plus u into dou v by dou x plus this one v into dou u by dou v by dou y plus w into dou v by dou z. But we know that v w component are 0 here, right? We only have u component, so we can take out all those things out now. Okay, we can take all the, because we don't have this u, only we have u component. So this v w component are 0 here. It's a unidirectional, so these directions will go out. So the acceleration is now, and it is not time dependent, so dou v by dou t will also go out. It's now just u into dou u by dou x, which is nothing but what is u? We already know 5 into 1 plus x square into d by dx into 1 plus, sorry, 5, 1 plus x square into 5. So if you differentiate that, what will you get? Already 5 into, sorry, this will be in the top, right? 5 into 1 plus x square, 1 plus x square, and if you differentiate this with respect to x, what will you get? 5 into 2x you will get, right? Because 1 will become 0, this will become 2. So ultimately you will get 5 into 5 into 2 will become 10 into 1 plus x square into x. So this will become 50 into x plus x cube, right? So that's the acceleration along the x direction. If you see the option A, 50 into x plus x cube is the right answer. So yeah, so it's very simple, right? Now since I referred to the formula and all to make you understand, it has taken this much time. Otherwise, you know the acceleration is equal to, for a unidirectional acceleration, u into dou u by dou x. That's it. Does it make sense? Okay, good. Let's move on to the next problem. This is an interesting problem. If you see here, the velocity is also a function of time, but unidirectional velocity, there is no xy dependency, y z dependency. It's an unidirectional velocity, but it's also a function of time. So it means unsteadiness. So velocity along the center line of the nozzle is given again. Very good. And so the velocity is varying like that. In the previous sum, they have given the area and volumetric flow rate. From there, we calculate velocity. Now they have directly given velocity here. Good. And the velocity is varying like this. Along x, it is varying like this. T also it is varying. And they have given t is time. X is the distance from the inlet to the nozzle. Now they are asking, find the convective acceleration, local acceleration, and then the total acceleration when the time is equal to 3. When the time is equal to 3 seconds at the location 0.5, what is the local acceleration, what is the convective acceleration, then you sum up that, that will be the total acceleration. So they are asking all the three. So since it is a unidirectional, our acceleration equation will become very easy. For example, like so now acceleration is equal to u into dou u by dou x. That's it. Plus dou u by dou t, because it's also the function of t. Because other times, if you go and see this formula, right, other times v, w and all is not there. It's the unidirectional flow, so that becomes nothing. Okay, that becomes 0. So this is your equation. Now this is your total derivative, total acceleration, and this part is your convective acceleration, and this part your local acceleration. First, let's calculate what is convective acceleration. Okay, how to calculate convective acceleration? U into dou u by dou x. So how do you, what is u? 2t into 1 minus x by 2l the whole square into dou u by dou x. How will you calculate dou u by dou x? I think it's very easy. If you differentiate dou u by dou x, you will get 2 into, so we have to go take this 2 here. So 2 into this entire term 2t into 1 minus x by 2l. Now you have to differentiate this term and this term, so that you'll get one more negative sign, extra sign you will get, right? So that is nothing but minus 1 by 2l. You have to differentiate this internal term. So if you multiply this u into dou u by dou x, which is the entire term, you will get now, and also you can substitute the values now, right? Because L is, you need to substitute what is the values of L. L is equal to 0.8, x is equal to 0.5. So now, and time is equal to 3. So let's substitute all the values. 2 into time is 3 into 1 minus x is 0.5 divided by 2 into 0.8 the whole square into, then this term 2 into 3 into 1 minus 0.5 divided by 0.8 into 2 into minus 1 by 2 into 0.8, right? So this entire term is the convective term. And if you multiply this term, the answer that we will get is minus, because the minus term is here, right? Minus 14.623 meter square per second, because it's acceleration. So now you have got the convective acceleration, right? Your convective acceleration u into dou u by dou x is equal to minus 14.623 meter square per second. But you also need to find out your local acceleration, which is dou u by dou t, and that is very easy because just t will go, right? If you differentiate it, what will you get? Just t will go. So 2 into 1 minus x by 2l the whole square, and 2 into 1 minus what is x? 0.5. 2l is 0.8 the whole square, and if you calculate, the value will come out to be very straightforward value, which is 0.945 meter square per second. So now you have got the local acceleration as well. So the total acceleration is now dv by dt is equal to local plus convective, which is, what is local? 0.945. What is convective? Minus 14.623. So finally you got your total acceleration to be minus 14 point minus 13 point, because you have to minus this, right? Minus 13.68 meter per second square, meter square plus meter per second square. Yeah, sorry, this is also meter per second square, which means what? The flow is decelerating because there is a minus symbol, right? So the flow is kind of decelerating. So the acceleration is minus 13.68 meter per second square. So this is how you need to calculate any acceleration for a fluid when it is in motion. Not only for acceleration, any change in property needs to be calculated using this. So acceleration is very straightforward. That's why we have calculated any fluid property change. Instead of this v, if you want acceleration, you substitute v. Otherwise, you substitute what is that property. If you want momentum, substitute momentum, whatever it is. But this is a very important approach in fluid mechanics world, because your continuity equation, momentum equation, anything, law of conservation of mass, momentum, energy, everything, we will use this approach, control volume approach. And when we use control volume approach, right, hereafter what we will do? Okay, when we want to calculate the rate of change of a particular property of a fluid or a particular parameter of a fluid, we just directly get into this equation, dou that property divided by dou t plus v vector dot del vector into that property. That's it. It could be anything. It could be mass, it could be momentum, anything. But now I hope you are very clear why this equation has come and how this equation has come, right? So with this, the basic approaches of fluid mechanics is done. Let's see some other topic in the next day's class. Thank you.
If you like this video, please like, share and subscribe my channel to encourage me. Thank you.